2025 is a special year for me because it will be 20 years that I'm in MR research. And I hear you say, "Ah, Francesco, you look so young, cannot be." It's true. It's 20 years. I started my PhD in 2005, and I've been developing methods, trying at least, mostly sequence development since then. I started kind of the first day. And I've been reviewing papers also for a good chunk of that time. I'm a good reviewer, so if you get me as a reviewer, I guess you will be quite lucky. I tend not to nitpick or bash people, and I always try to find the value in the study that you have run and in the data that you have acquired. So this is to say, however, that I know you, because I've been you, and maybe you have been me if you're a bit older. But I know how we run things, and I know when things are difficult, and I know how we did things in the beginning, and I know how people still do things. So, well, I don't have a financial interest, especially in this presentation. As Sophie, I'm not a statistician. I think this was abundantly clear. I'm a statistics aficionado. If you want, this presentation is also available as under Creative Commons license. There are a couple of things that are copyrighted, but they're well indicated there. So feel free to come back to me for some slides. So part one of 175, general introduction. So you have obtained your first map. So we are talking about quantitative, no? So you have obtained your first map. I've done it. New sequence, new readout, and there is a map, and it makes sense. So how did I do that? So I started with an idea. I said, yeah, let's do, inversion recovery balances FP for cardiac. This is something I've done in the past. So I went to my computer, thought about it, hacked that. I was using IDEA, Siemens IDEA, fighting with it. And then the first image looked crap. And then I went back to the computer and tweaked that and made it a little bit better. And then the images looked a little bit better, and then a little bit better, and then a little bit better. And then finally, I get a very nice image. And I celebrate, because now I have the image. And this is what it's all about, no? So what do we have now? I have a sequence, and I have a protocol that I have tested on my volunteer, and I have a reconstruction, so I have my algorithm sorted out, and I have these values that make perfect sense. First, they didn't make much sense, but then I saw that, well, with a different flip angle, different TR, then of course they fall into the range in the literature, so happy. So, ready for publication. Well, not quite. Slow down, tiger. So, scientific method has two steps. Everybody knows that. One is the full around. Actually, it's not full, but for keeping it PG. It's full around, and I was definitely in the full around stage. I hacked things, modified the sequence, changed the parameters until I got the image that I really wanted. But I still have one important step, which is the find out step. So how do I find out if my method really, really works? And then, of course, it always happens. You send your paper. Let's say I send my paper now. And there is always one reviewer. No, one reviewer is nice. I would be the nice reviewer. But there is someone else that always says, ha, this is not true science. Because it cannot be true science if there is no statistics. And it also can't be statistics if there is no p-value. So then you realize, okay, I need a p-value to get this published. How do I get a p-value? I mean, I have one subject, I have lots of voxels. Let's do a t-test between gray and white matters, for example. It's different, then I get p-value, then I can publish it. Okay, so I will try to give you some practical information how to go about and respond to this reviewer, and also maybe do what they want, but also not do what they want. So let's take a step back. Now we go really basic statistics. So I have these two distributions. And the p-value is smaller than 0.001. So how do you define these two distributions? These distributions are different. Who says that they're different? Raise your hand if they're different. Okay, very few people, like 4 people say they're different. With a p-value, it's a small p-value, guys. They are different. They have a different mean, there's a small p-value. So the two distributions are the same. Who says that they're the same? Lots of undecided people. I mean, do you know statistics? I mean, it's a p-value. It's small. Okay, they are different. I tell you that they are different. Now we have a p-value of 0.02. And the mean is also kind of the same, no? Still 1009, 1039. The two distributions are the same or different? Same? Who says they're the same? Somehow fewer people. So a bigger p-value, but fewer people think they're the same. Well, different, everybody else, no? Okay, everybody else different. So again, these two distributions, p-value is 0.17. So now these are for sure, say it together. The same, yes, they are the same. The mean is 1007 and the other is 1070. There is this small thing that I didn't mention, this n here. Okay. So in reality, the two distributions are different. So the means, they are two simulated distributions. They're generated with two different means, 1000 and 1050. Standard deviations are the same, 100 and 100. The only thing that was changing was the number of samples that I took from these distributions. So remember, so the difference in means is exactly the same for the 3 examples. And the 3 distributions are all the same distributions, and they're all different, but the p-value changes a lot because I changed a lot the number of studies. What does the p-value tell us then? So the p-value is a probability of observing a specific summary of the data, or a more extreme summary of the data, given an assumed distribution. All on board. So it is not the probability of my hypothesis. And it's not how big the difference is. This is very important. So a very, very small p-value doesn't mean that there is a big difference. It just means that you had enough points to demonstrate that there was a difference. A summary, so when I'm talking about summary, it depends on the test. For the t-test, which is the most basic test, it's a mean. So we are evaluating the means. The t-test is telling us that there is a probability of observing a mean that is as different from our hypothesis as the mean that we are observing. So the t-test, I assume that 2 distributions have the same mean, and this is my null hypothesis. And then there is a probability of me observing the difference in mean that is, so the difference mean that I observe, how probable it is that it happens under random chance. So if the p is very low, then probably we have different means. And this we were seeing, you know, we had different means actually in the distribution. We had 1,000 points and the p was very low. So we were quite confident that the 2 means are different. And the p is high, however, doesn't mean that the 2 distributions have the same mean. It just means that they can have the same mean, but quite likely you have too few data points. And we saw exactly that. No? The distributions were the same, but with 10 data points, the p-value was non-significant. Non-significant. This is also something interesting. So why do we consider p less than 0.05 significant? So choice number 1, the distribution of p-values has a sharp edge at 0.05. So it changes a lot, no? From 0.04 to 0.06, it's a completely different word. Option number 2, 0.05 guarantees no type 2 errors, so no false negatives. Option number 3, someone came up with it 70 years ago and everybody kind of stuck with it. So Put your fingers in the air. Wow, you're all educated. Well done, guys. This was Fisher, I mean, smart guy. And 1950, so a bit before I started my PhD, if you remember. He say that it is convenient to take this point as a limit in judging whether a deviation is to be considered significant or not. Formally regarded as significant. So actually, when you read these, he never really says true. So it doesn't say that significant means true. Significant means interesting. So say that, look, if it's less than 0.05, let's try to find out what is really going on. But anyway, somehow this became the threshold for truth. And that's why reviewer 2 always asks you, but is your p-value less than 0.05? So what if the p-value is less than 0.05? Reviewer 2 is happy, you publish your paper, but what does it really mean? So you have a lot of data points, your p-value is very low, and the mean in this case is 1,000 versus 1,007. And the difference is 0.7%. And it's significant, but it's 0.7%. It is significant because, by definition, is it meaningful? Well, maybe. Probably not. I would say if this is, if we're measuring T1, I probably wouldn't care about the difference of 0.7% in T1. But if I measure enough people, then I will get this significance. But the difference is still the same. So meaningful, if something is meaningful, there is no statistical method that will tell you this. This is you who have to decide whether something is meaningful or not. And you meaning you're the researcher, you're the clinician, you the person that knows what we're talking about. So if we want to detect, if we think that 0.7% difference is clinically significant, then of course, by all means, go and do that. But the fact that just the p-value is very low will not tell you whether it's clinically relevant. So, okay, let's be concrete now. It's a lot of blah, blah. I measure a certain number of subjects with my method and the reference method, and the difference is significant. This is something I see all the time as a reviewer, really. I mean, if you have reviewed a quantitative paper, even if the paper is good, the method is really good, a lot of people just do this. They measure the values with my method, with reference method, and they do a t-test. So, is it helpful? So, no, it just means that you have measured enough patients so that you can detect a significant bias between the two methods. But 90% of the time, I don't care about that. I mean, the bias, I want to know if the bias is big or small. I don't want to know if it's significant or not, if you measured enough people. So we will come to this, and we will see it's much more useful to characterize this bias rather than saying it's significant or not. This p-value just doesn't tell me anything. So when I design a study, and in this case we are talking about quantitative imaging, I design a study to evaluate my method. So the right way of doing things is you start with a hypothesis. So what do I want to show? I want to show that my method is as good as another, is better than another. But exactly what metric do I use to show that? And then I choose the metric, no? It can be SNR, can be distribution of T1 values, whatever you want. Then you decide the analysis plan. Okay, to show that I have this difference, then I will use this statistical test. And because this statistical test will tell me this. For example, in the bias case, I don't, using a t-test is not the appropriate test. I want to do a correlation analysis. I want to do an agreement analysis, not necessarily a t-test. And then after I decide which test to use, I have my acquisition plan, and I start acquiring my subjects. So first of all, you have to understand what will go in your paper. So what value are you going to show in your paper, how you obtain this value, and on what population. And then you go and measure the population appropriate to that. What happens a lot of the time, and I've done it in my 20 years, I've done it myself, I have a method. I start with acquiring a bunch of data, and then, okay, I have all this data. What do? Okay, let's run statistics on it. and then I get a bunch of p-values, and I say, okay, what can I say with these p-values? They're different, I guess. But this is actually not really the proper way to do. And I would like to show you the proper way, and it's not Francesco who says this. I mean, no, physically yes, but there is a base why I say this. So now let's go to section 2. We have, I hope I haven't bored you so far, hopefully not. Are there questions regarding section 1? Let's keep it light and interactive. Oh, someone has a question. Fantastic. It was rhetorical, actually. It was not inviting questions. I want to go on.
Just assuming the distribution from which you drew your examples earlier on was normally distributed,
yes.
Right? Yeah, so that's another point. Is your data normally distributed in the first place? But
we can talk about it. I have opinions about that as well. I mean, I have a lot of opinions, you can imagine. By the way, all these graphs are actually, there is a GitHub link in the end. Initially, with the reproducibility study group, we thought about this session. We wanted it to be interactive and that you could follow Jupyter Notebook and so on. But then it was a bit complicated to organize. But there will be kind of a companion R markdown. So if you don't know R, learn R. It's cool. And there is a link in the end. So you can prove that these distributions are actually normal and everything. So let's first describe our method. So now we have our quantitative method, and the first thing that I want to report for my method and what you should report from your method is a mean and a standard deviation. So I do a first experiment. And now let's be concrete. So guys, if I review a quantitative paper, I want to see at least this. Run a first experiment and run it on a certain number of subjects. Please, not just one. Don't just show me one map. Show me at least a few subjects. Or a certain number of phantoms. In this case, you only need to scan them once, and with only one method, only your method, not even reference standard, doesn't even need to exist. So draw your ROIs. Assume that there is a constant true value in one ROI. So let's try to put them in the white matter. Assume that everything is homogeneous in the white matter. Assume that everything is homogeneous here in the gray matter, so that one value of one ROI, we can imagine that it's the T1 value for white matter, for example. What should you report? So report the average for each ROI. So average value for white matter, average value for gray matter. This is the basics. And then report the intra-subject variation, which means basically the standard deviation inside an ROI. This is quite interesting, but maybe not even that much. What is more important is the natural variability, so the variation across your subjects. This is very important because my T1 of white matter might be a bit different from the T1 value of your white matter, so it's important to know what the standard range for this is. How do you calculate this? You calculate the mean. So in every ROI, you sum the values of the pixels in the ROI and you divide it by the number of pixels for every pixel that belongs to the ROI. And then you calculate the overall mean, which means you can just do let's assume that we're having the same ROIs everywhere, just do the sum of the means and divide by the number of subjects. So we know white matter in subject 1 has 1,040, white matter in subject 2 has 1,045, and so on. And then you can do. And then you calculate the inter-subject standard deviation. So you take these means that you calculated, and you calculate the standard deviation. Everyone knows how to calculate the standard deviation, I hope. Easy. There is this -1 because it's estimation of the standard deviation, degrees of freedom, blah, blah, blah. Ask your statistician. Okay, this is important because now the mean is our reference value for a specific ROI, meaning white matter, no? So it's our reference value. We know that with my method, I am measuring a certain value of white matter. For example, this comes from this paper here. T1 in healthy subjects had 191, white matter in MS patients 994. So this method has these values. And it's important also to calculate the standard deviation because if you divide the difference in means by the standard deviation, you get this number, which is called Cohen's D. That's why it's called, I have a D here. And this is the effect size. And always report effect sizes, guys. Don't skimp on effect sizes. It's important for sample size calculations because this is what goes in your sample size calculation when you want to do then a clinical study. So this is, remember this. But it's just not enough. You also want to give a confidence. So the standard deviation is not the confidence. You can have a confidence that your average T1 across all your population is, your confidence is higher than the standard deviation in the population. And this is a central limit theorem. It's a very simple theorem. Very simply, the standard error, so the confidence in which you have, in which you calculate the mean, is the standard deviation divided by the square root of the number of subjects. And if you want to calculate your confidence intervals, it means I'm confident that the average T1 value for white matter in all this room is between this and that. Depending on how many people I sample in this room, then I can calculate it here. Basically, I multiply the standard deviation by this value, and I get the 95% confidence interval. So if you see if you are scanning 6 subjects, then you have more or less a 95% confidence interval for your mean that is more or less the same as the standard deviation. The more you measure, the more accurate your mean estimate comes, so it can become very, very accurate. So even if you have a large standard deviation, you can still have a very accurate measurement of the mean. For example, if we have an average of 891, like before, standard deviation 90, number of subject 20, our confidence intervals are plus minus 0.47 from table before, blah, blah. The true mean is contained between these two values, 849 and 933. And this will give you, so 95% confidence that my mean in the population is contained in these values. So don't report me the mean to 27 significant digits, because your error can be between 849 and 933. It's large. It doesn't make sense to report your mean that you find as 891.45684, because the fork, the interval that you actually have is very, very large. I would say it's okay to, there is no really hard rule, but it would be good if you put your 95% interval. Nobody does that, but I'm telling you, you should. But it's not just that. You also have a confidence for the standard deviation. And when we are using it, the standard deviation as quality metric, and we are saying, look how nicely precise my method is because the standard deviation is very low, then we also need to make sure that we are estimating our standard deviation correctly. And nobody really talks about it, but it's a bit more complicated, the confidence for the standard deviation. It's asymmetric. But if you only measure 2 subjects and you evaluate the standard deviation from these 2 subjects, I mean, technically you can do it, but the standard deviation that you calculate has a confidence interval that goes from 0.5 of what you measure to 32 times what you measure. So if you measure a standard deviation of 10 with your 2 subjects, actually the true population standard deviation might be, I said 10, might be 320. So you need to have a certain number of subjects if you want to give any confidence in the metrics that you express. So you always should relate what you tell me in terms of mean and standard deviation, and you should give me the confidence intervals for the estimation of the mean and for the estimation of the standard deviation that you show me. People don't tell you this usually, but it's important because otherwise you can always calculate the standard deviation, and you always get one mean, one standard deviation, and you completely lose the focus of how many subjects you scanned. But if you show the 95% confidence intervals, then it really separates the good high-power studies from the low-power studies. And we're just talking about descriptive values, no p-values, but the confidence that I can give you in these values. So this is the first part, describing just a mean and a standard deviation. I would like also to see confidence intervals in the mean and standard deviation that depend on the number of subjects, and you can use these tables if you want to relate your confidence intervals to the number of subjects. Questions for part 2? You learned the lesson that it's actually rhetorical. I don't want questions. So part 3. Now, promise almost the last part. Characterizing. So this is not a characterization of my methods. I'm just describing the population as I measure it with my own method that I just developed and I just measured a bunch of people with. And it's already important information that should go in your paper. For properly characterizing your method, now we're talking about, is my method good or is my method bad? Spoiler alert, there is no statistical method that can tell you if your method is good or bad, because that depends on the clinical application and what you actually want to see. Might be good, might be bad. But anyway, the important literature for this is this paper from the Quantitative study group that came out a couple of years ago. And this paper, I would say, it's a little bit, I don't want to say simplified, but more accessible and practical version of a bunch of other papers that are published in statistical methods, in medical research by the Quantitative Imaging Biomarker Alliances. So a lot of things that are said in this paper are actually explored in much more detail in these other papers. These are just 2, there are more of them. But this paper is really, really good, and I'm going only to talk about a small part of it. There is more about that. But what is important in this paper is that when you want to characterize your method, so you have your imaging method, you want to tell me if it's good or if it's bad, it means you have to characterize 2 things, bias and precision. And you can imagine that what you measure is this y, and what you want, so what you get out of your method is this y, and the x is the true value that you're supposed to be measuring. So you have these 2 factors. One is a constant bias, and one is a regression slope. So how, if there is a difference, a systematic difference, and if there is a non-linearity or a slope that is not 1, so it overestimates, underestimates some values. This is the bias, or the bias profile, and then you have an added error, which is your precision profile. And there are ways to measure both the bias and the precision, and there are more ways, and I'm going to just talk to you about the simplest ways. And it's already more than enough. Bias. To measure bias, you need a reference method. You need to test something that covers the whole physiological interval. So if you know that if you want to use your method to measure patients, and you know that patients have a very different T1 value than your volunteers, you should also include patients in your interval. Or even better, use phantoms that cover the whole. Paper says at least 10 points. And yes, you can do it in vivo or in vitro, but the idea is that you measure your method and the reference method. And then you can use various things. What I suggest you to do is just do a Bland-Altman plot. And this is a plot the average and the difference with respect to a gold standard. So I have plots here. You have the average the average of the 2 methods on the x-axis, and on the y-axis you have the difference between the 2 methods. And then you see there are lots of lines, because the Bland-Altman plot gives you the blue line, which is the average bias, so your constant bias that you get, the average difference between the two methods. If your method is always saying 10 milliseconds longer than the reference method, for example, it would show here. And then you have these red lines that are limits of agreement. These are calculated in a way that 95% of the measures of the data you measure just falls within these limits of agreement. And this is great because if these data you see are more or less all the same, then it means that the relationship between the reference method and your method is kind of linear because your noise doesn't get amplified with larger values or whatever. And you also get a feeling of how wide the difference between the reference method and your method can be. So you can say here you have 10 milliseconds or here 40 milliseconds. It means that when you measure things with your method and when you measure things with the other method, the maximum difference can be up to 40 milliseconds. And you don't need a p-value to know if it's good or not. You need your clinical expertise. You need to tell me, is 40 milliseconds enough to detect what you want to detect or not? And there is no p-value involved here. You don't care about that. You just want to know how different this is. But then you see I also added some other lines. It's a bit messy, but these are actually the confidence intervals of the limits of agreement and of the bias. And these are the same distributions, but increasing the number of subjects actually gives us much narrower estimates of the limits of agreement. So we are estimating from our sample these limits of agreement, but the real ones of the population might be much broader if we have very few subjects. So you should also indicate that, look, I measure 20, but it could be up to 50. And these, there is a code available on GitHub. I will show you later. You can do that, plug in your data, and it will give you the Blonde-Altman plot with all the limits of agreement and the confidence intervals of the limits of agreement. I think this is already great. This is a very, very nice characterization of the bias. You can do much more stuff. It's in the paper, but if I see these, I'm happy as a reviewer. So if there is no trend in residuals, it's linear, as we said. Just as I mentioned, I don't care about p-value in this case. I just want to know how big the limits of agreements are to have a feeling of how much I can trust your new method or my new method with respect to the reference interval. And is it good? As I said, it's a clinical decision. It's not a statistical decision. It's a clinical decision. You tell me it's good because my differences are up to 20 milliseconds, and my difference that I want to detect are 100 milliseconds, so this method is good for that. And finally, precision, closely related to repeatability. So now we are comparing with a gold standard, but the precision is related to how much my method is stable, and I can measure this. If I measure the same thing again, how much will it vary the outcome? We can talk about repeatability and reproducibility. Usually repeatability means that I'm scanning things in the same conditions. Reproducibility, the conditions are different. There are different definitions of those, but these are kind of the most accepted. This does not need a reference method, so if your method is completely new, measuring something completely unheard of before, then you can still do this, but you need to scan people multiple times. So you need to scan the same subjects at multiple time points because we want to see how repeatable your stuff is. Sorry, it's a bit more boring, this part than the part before, but I think it's important that I don't want to remember all these formulas. They're actually simple formulas. You can come back to this presentation afterwards. You can read the paper, but I want you to understand what are the minimum things that should be reported in a paper. So the precision, you measure the same subject twice. This is the easiest case. Then you estimate the per subject variance. Basically, you take the difference between the first measurement and the second measurement squared divided by 2. And then you can pool the variances. So you do, it's average of the variances. So you don't do the average of a standard deviation. This is something that other people do. Don't average standard deviations because it's a quadratic moment, and you should average the variances and then take the square root of that. So if you take the square root of the pool variance, then you get the within subject standard deviation. And this is kind of the thing that you want. This is the precision profile. Let's put it like that. So it's very easy, but the within subject standard deviation is basically the measurement error that you can get when you scan the same thing twice. So you can calculate then this repeatability coefficient, which is just this number, 2.77 times the within subject standard deviation, and this is kind of the maximum, 95%, but let's say the maximum difference between two measurements, two repeated measurements. So again, if this repeatability coefficient is 100 milliseconds, it means that kind of your precision is 100 milliseconds. So the maximum difference between one measurement now and one measurement tomorrow will be 100 milliseconds. Again, no p-value. You tell me if it's good or not. It depends on your clinical application. Again, like before, this is a standard deviation. So the standard deviation is uncertain. Same table as before. If you have few subjects that you repeat, then you insert the uncertainty on your within subject standard deviation can be very large. So you can say, I have a 10 millisecond precision, but it's actually 320 milliseconds precision, or it can be up to 320 milliseconds. And actually the Kiba profiles say that the accurate estimation can be assumed if your number of subjects is more than 35. It's a lot. You don't have to scan 35 subjects to make me happy, but at least discuss that. Even the paper says that 35 is kind of aspirational, and you do it with meta-analysis, so you don't do it with a single prospective study, but at least don't do 2, don't do 3, because you see the uncertainty that you get in your estimate is very, very high. So you tell me 10, it can be up to 60. It's a lot. I mean, it could be fine if you have a huge effect size, but you know. Okay, we're wrapping up. I have 5 more minutes. I think I'm on time. Before I wrap up, any questions? I scared you, huh? We'll have some kind of questions. So, original pipeline. I have my method. I optimize my protocol. I test it. Is the quality okay? No, then I do more method development, protocol. Then finally, I get one image that makes sense, and I publish. Not so fast. So this is where we started from. It's not time to publish yet. You should do these as well. It's a lot, I know. So this is also helpful if somebody wants to take a picture. I saw people taking pictures. This is helpful. Test your method in n subjects, report the mean and standard deviation with confidence intervals. Then, if you have a reference method, also measure with the reference method, same subjects, and do a Bland-Altman plot. If you don't, whether you have or not have, do also a test-retest analysis and try to estimate a precision profile. And that's it. I mean, it's not too bad. You have to study, you have to fix a protocol, and then scan 10 subjects, and then scan 10 subjects again, and that's it. It's not too bad. But this is where things might go wrong. And it's easy to obtain one good image. Obtaining consistently good images when I fix my protocol and I cannot go back to my optimization is harder. And, but this is exactly what we want to see. So clinically nobody cares if you obtain one good image once. It's better to have 100 average images that the doctor can rely upon than a method that produces one good image every 100. So there is no absolute threshold. So as I said, I cannot tell you if a method is good or bad. It depends on your application. What I say, at some point, you have to say, my method is just good enough. So you don't say my method is good enough for this. And then, of course, coming back quickly to this, what happens if my method fails here? And now it's the interactive part. What happens if my method fails validation? So now you have one good image, and you test it in 10 subjects, and then the numbers are all over the place. It happens, trust me. So option number 1, hide the validation data and try to publish the methodology only in a lower impact factor journal. Variant of 1, just do not run a validation study. No, if you don't, in Italy, I don't know if there is the same in English. If your eye doesn't see, your heart doesn't hurt. So just don't run a validation study. Try to submit it as soon as you have it, and it's someone else's problem. They will characterize your method if they want. Or option number 3, scrap the whole project after years of development, because yeah, you made all the effort, but it didn't turn out great, and that's what you do. So who's for option number 1? Raise your number. There is someone for option number 1. Great. I did it as well. No, it's not true. All my papers are perfect. So, is there another way? Well, of course, you can try to publish your validation that is not so great. You can try to publish it as a negative result in a journal. It's going to be hard. People are going to say, yes, but why would I publish your method if it's not good enough? Some journals even say, so Nature Methods actually explicitly says, is Nature Methods? I think it's Nature Methods, or plus one, that you can only publish a method if you demonstrate that it's better than an existing method. So for me, it's something inconceivable. So it explicitly does not accept negative results. But this is why people at ISMRM, and we are trying to replicate this at ISMRMB as well, are trying to push register reports for this kind of method. So we cannot have a paper yet. It's coming soon. I see editor-in-chief, at least, in this session. So probably they will get inspired by that. But you can have it as an abstract format. And I really encourage, if you have a quantitative method, publish this first, so submit this first part up to your first image as a register report, as a stage 1 register report. And then you say, I'm going to do the validation afterwards. And if the abstract is accepted after you have your first image, so your method is promising, then you can do the validation and it will be published whether it's good or not. And it's only evaluated based on the plan, not good or bad results, and we encourage rigorous testing. So you do this, the quality is okay, submit it as stage 1 register report. And then whatever happens here, you know that the paper will be published with a fair assessment of your method, and then people will decide whether it's good enough or not. As I said, I'm not telling you what is good or what is bad. I'm telling you, give a fair assessment, and then the clinicians and the clinical community will decide whether it's good enough or not. Okay, this is it. Promise, just last slide. All the R code, including the Bandman with confidence intervals, are available here. F. Santini, my name, ISMRM 25. Quantitative method must be properly characterized. Please, try to publish papers where you give at least some characterization. I gave you 3 things you need to test. You tell me the variability of the population, an idea of the bias if you can, and some idea of precision. And the sample size is important. You don't have to scan hundreds of subjects, but at least please deal with the problem. Know that small sample size lead to bigger uncertainty. And yeah, I don't care about statistical significance, at least not in this context. So if the reviewer tells you, I want to see a p-value, you say, no, Francesco told me it's not necessary to have a p-value. Okay, Thank you guys for listening to me. Thank you for my group.